as evident from the title of my presentation, I will not be talking about carbon. And just to change the flavor, let's talk about water, because most of the presentations we were hearing, one thing I deduced that I do not know what is going to change in climate change, but water is going to change. Either it's going to go wetter or drier at some places. And that's why I think it's important that we look at the water footprints of different crops, which we are thinking about in biofuels, and look at the implications. What could be the implications of these crops? And to start with, I would say that we assume that biofuels have, and we believe now, there are so many presentations already, we have to believe that biofuels have potential to mitigate climate change, and it could be due to lower emissions or potential for mitigation of droughts and desertification by planting grasses on the degraded lands or deserts. And there are benefits which we might be gaining by adopting cellulosic biofuels compared to the grain-based biofuels, which again includes carbon sequestration and water quality benefits and all. Well, by this time, we have already seen that global warming is going to be hit through water, and that could be because so far what we know of climate change is that there will be changes in hydrological cycles, and that is the only effect which we know for sure would happen. That would include that we would have glacial melt and sea level rise, and changes in the water temperatures, which would affect aquatic life. On the other hand, in the terrestrial environment, we would have serious or frequent extremes, for example, floods, droughts, and typhoons, to generalize. Water footprint assessment, the concept of water footprints is that we look at how much water is used by a particular product in its life cycle. That means when we generate something, or make something, how much water is used to make that product. For example, a burger, how much water would a burger take to come to McDonald's and then be eaten? For example, 4,000 liters for a burger is its life cycle water consumption. In case of biofuels, I will not talk about the life cycle assessment, but we already know that 80 to 99% of the water in biofuel life cycle will be used during the production of biofuels in the field. And that 99% would be in areas like California, where there's no water and there's high temperatures, and 80% in case of Michigan, where it's getting to be wetter. And it's to start with climate change and to make my case that water is important in climate change. There are a number of questions which come into my mind, and those questions are that we have different choices for biofuels at this time. We have different cellulosic crops, and then food grains, and so we have choice for energy source, which would have different water implications. But when we talk about climate change, how would this balance between the biofuels and food production be affected when we talk about water footprints? How much consumption by particular biofuel crop compared to a food crop occurring? And if there's climate change and all these things happen, which I talked about earlier in my slide, and if it comes to choice between food crops and biofuel crops, how would we prioritize between the production of food and biofuels? These are important questions. And to start with, I would say that we know already plenty that electricity generation takes less water than ethanol and then biodiesel. And cellulosic ethanol, again, would be less water expensive than the grain ethanol and algal ethanol. There are very, very few evidences about the algal ethanol, but the evidences which are coming out, algal ethanol will take, the only implication of algal ethanol production would be huge amounts of water which are required to produce it. And in this background, I would also say that we know that corn and sugarcane take very less amount of water compared to soybeans, just to say, for example. And hydropower and sugarcane biofuels, corn biofuels, they take more water compared to any other source of energy. And to understand all these relationships in the background of climate change, I think it is very important that we understand the water bioenergy nexus, and there are a number of factors which control all this water footprints and how this water bioenergy nexus goes ahead. And to understand that nexus, we have various studies that KV started at different scales, including the scale of fields and small plot fields, which are around 1 hectare in size. My previous speaker talked about those sites, and collecting the data from all those sites and these studies, I would like to look at our choice of crops, how water footprints will be affected by the choice of crops. What kind of biodiesel, whether we want to make ethanol or biodiesel, or we will go with the cellulosic or grain-based crops. And there are a lot of choices. Also because land is limited. At this time we are saturated. We are at the saturation level where we can use our land. 50% land in United States of America is already under agriculture. And to avoid the competition between food and fuel, we will have to also look at where we will grow these biofuels. So land quality and marginality is another issue which will affect the water footprints, the production of biofuels. And how we manage these would also affect the water footprints and also the water quality. To start with, this is the data which we are taking continuously in our experiments. Every hour collection of how water is moving in the soil profile. And for example, I have this soil profile which goes down to 1.3 meter, and every 15 centimeter we have water signatures coming out, and we can tell by looking at these signatures that how water is moving down and whether enough water is moving down to the water table or not compared to the other crops. And so we have 10 systems. For example, in corn, I can say that this is the soil water content, and these are the days of the year. For example, I can say that at 50 to 60 centimeter layer depth, there's plenty of water during the growth of the corn, but it was not utilized. And the reason for that is because we already know all these things, water footprints would be affected by either roots or canopies and management. Third factor. Deeper roots would be better utilizing the water. At the same time, there will be lesser recharge to groundwater. And denser canopy would be very effective in intercepting the light. So we would have more biomass, but we would also have more interception losses and less recharge of water to groundwater. Compared to corn, we have very effective utilization of water in the miscanthus, which is one exotic grass, and poplars, but at the same time lesser recharge to groundwater. Now on a bigger scale, when we look at, my earlier speaker talked about these sites. These are sites which range from 9 to 21 hectares on the landscape, and 3 of the sites converted from corn to soybean this year, agriculture to soybeans this year. Other 3 converted from CRP lands, which were under CRP program for last at least 10 years, 5 to 10 years, and 1 reference site at the same locations. These are the best locations we could get on a landscape level. And what I try to do is to look at how marginality of land increases or quality decreases, and how would it affect the water footprints. And when we look at these lands, these are the graphs which show how much biomass we will be getting, how much grains we will be getting, first of all, from these, because these lands were converted to soybeans. They show that our sampling, 2 or 3 samples in each field, will not give us a clear picture or how much we will get, because the production would certainly depend upon the quality of this land, whether it can support that much or not, and inputs. So looking at these scenarios, in June, first of all, I evaluated using different parameters the marginality of land, how marginal a land is. Because these lands always qualified for CRP program, that makes them marginal lands, first of all. And even the agricultural lands which were under agriculture, they qualified for being marginal land, like CRP program, but they were not. And management can have a great effect on the land, basically, because inherently when I calculated using the Sergo database, the marginality of land, that included slope factor, soil quality, and land capability classification. In CRP lands, there's a better soil quality already within 5 to 10 years that included almost everything: carbon, nitrogen, phosphorus. Pools have increased, and erodibility has decreased. And erodibility, just by planting grasses on these lands, would be decreasing 80 to 90%. And water footprints, water footprints varied a lot. Like for example, for grain production, we had 3,000 to 9,000 cubic meters of water per ton of biomass production. And for grain production, for biomass production, we had much lower water footprints, obviously, because we're using all the biomass for energy production, including the store. And yeah, but in general, the relationship is not very strong. 7 sites not enough for finding out the relationship. But in general, water footprints decreased with the marginality, and the reason for that could be that stress management by the plants, actually. And one interesting thing which came out from the studies, the same study, is what is the water footprint of soybean compared to, because one of the sites was under burn grass, CRP grass mix, and we found that if the same land is used and the biomass produced on this land is used for generating energy by burning, the water footprints are going to be 10 to 20 times lesser. So if all the biomass is burned, instead of making ethanol from the grass or making biodiesel from the soybeans. Yeah, in general, and for both of them, burning is the most effective energy production technique compared to ethanol production. And management would have large implications for water quality. We're already seeing that in switchgrass plantations where we use different rates of fertilizer application, a lot of fertilizer moves down to the groundwater. The profiles are so porous. At least here we have the sandy clay loams. But in any soil, ultimately, fertilizer which is not used by the plants would move down either to our streams or to groundwater. And so management would also have large implications for water footprints in water use by biomass production and by pollution of streams and groundwater. And with that, I would say that besides all these things which we're looking at, we already know there are a lot of uncertainties. And those uncertainties are in the backdrop of uncertainties of climate change effects. And there's a technology change which will take place in future that would affect the water footprints, also other things. And then these effects will be regional, and there will be incentives and programs which would define biofuel landscapes, which we do not know, which these incentives programs are not there yet. And that's it. Thank you.
Time for questions? You mentioned burning.
Yes.
What is that? Is that some form of chamber that you burn in?
Well, so yeah, for example, burning. So I did not do the burning myself. I did not burn it. So if we go to the Department of Energy website, they have all these conversions. I just need to, for example, ethanol. I did not make ethanol from these grasses. We put in the sugars, different sugars, which are available from the plants. How much is the sugar would define how much ethanol you would get. It's a simple conversion, and also the burning. So I just use their conversion, which they have calculators on their sites.
How many seasons have you looked at thus far for your results, and what about climate variability?
Yeah, so it's just one season.
Just like
yeah, just
so
previous speaker.
We'll have 4 or 5 then?
Yeah, in general, for example, different crops, we can already look at the data which is available worldwide. I mean, we just have to calculate the evapotranspiration coming up here. But for example, marginality thing, which I talked about, we just looked at one season. We do not have any data. But it looks very interesting. Thank you.
Okay, thanks, Ajay.